All right, good morning, sugars. I told everyone that I'm skipping around on these notes, so we're looking at 11.1 notes. I will be skipping around a good bit, so just try to follow along. So we miss you guys. Hope you're back soon. All right, here we go. Let's rock and roll. So, significance testing. Why in the world did somebody come up with this hypothesis significance testing? Essentially, what they're saying is, I don't believe you. I know that that's supposed to be a 16.9 ounce water, Katie Perkins, but I don't believe that they're really filling it to 16.9 ounces. I know every time I open that water, guess what happens? It spills over into my lap, so I believe that they're filling it to a larger amount than 16.9 ounces. Or maybe that water level is always so low it's near like the label and you're like, that's wrong. I know that's not 16.9 ounces, okay? Or you open your bag of Lay's potato chips and you open it up and it looks halfway full, right? You're like, I know that they're underfilling my potato chips, and I'm so angry that I'm going to do a significance test and I'm going to prove to them that they're wrong, okay? So a significance test is being done because you do not believe what has historically been believed or told to you, okay? So this is historically what we've always believed, but now I don't believe you, so now I'm going to run a test to prove to you that you're wrong and you need to change what you've always believed to be true. Okay, so that's why we're doing it. We're running a significance test because we do not believe what has historically always been believed. Okay, it's a z-score and it's a p-value, and that's pretty much it. Does that sound fantastic? All right, so that's it. Okay, so our setup is going to look a little bit different. Now we have some stuff to write in our setup. We have a ho and a ha. Okay. So we have an HO, which is your null hypothesis. That little sub-zero, your HO, this is your null hypothesis. There are some great AP Stats Guy videos on significance testing, by the way. So if you want to go pull up AP Stats Guy, AP Stat Guy. All right, this is your null hypothesis. This is what you have historically believed to be true. But now you don't believe it anymore. So you're going to use your statistical savvy to try to disprove your ho. Okay? All right. That's H. That's a little zero, null hypothesis. And then we have our ha. And our ha is our alternative hypothesis. Now, this is what my belief is before I even start the stats. I believe that they're overfilling the water because it's pouring out in my lap every time I open it. So I would make this a greater than. I now believe, okay, and I'll get into the lingo of this, but I now believe that it is not 16.9 ounces. I believe it's greater than. Now, I'm not going to bust out and be like, I know it's 17.1 because I took one sample and my one sample's so accurate that it's 17.1. No, that's insane. You take another sample, it's not going to be 17.1, but I believe overall it's not 16.9. I believe it's greater than 16.9 ounces, okay? So at the beginning, you have to decide, is what is historically true? Do I believe it to be less than that, greater than that, or not equals to? Okay, so it's going to be one or the other, okay? So that's what we're going to put underneath our setup. Our conditions, guess what? We're still going to sin our conditions. So I've started you guys on sinning, and you're going to still sin. Your sin remains the same. It's not a different sin, okay? So you're still sinning the same. Your arithmetic is going to be a z-score, okay? So it is your estimate minus your parameter divided by your standard deviation. So if it's a z-score, then it would be x bar minus mu all over sigma divided by the square root of n. If it were a t-star, it would be x bar minus mu all over s divided by the square root of n. And if it were an easy peasy that is going to be your estimate, p hat minus p, all over the square root of p, 1 minus p, all over n. So y'all have seen these formulas before. I don't know if we've actually ever used the t star like that, but it's pretty logical, right? Isn't that what we use for a t star? Use standard error. This is what we use for the standard deviation of p's and p hats. That's our standard deviation for t stars, right? Standard error. And that's what we've started with many years ago, okay? So all we have to do is come up, that's our arithmetic. We come up with our z-score. We also come up with p-values, bless you, that are associated with this, bless you. And then we make a decision. We either reject the hoe. Always reject the hoe. That's really important. Okay. Reject the hoe. I did have a stat shirt, so, reject HO. Or you fail to reject. And this is important. I know this sounds silly, but it's really important. You never accept the hoe. You never accept it to be true. Okay, we're little squirrely statisticians. We're never going to say, just because I couldn't prove that you were wrong, I'm never going to say you were right. Okay, just because I couldn't prove that it's not 16.9 ounces and I didn't have enough evidence, I'm not going to say that it is and accept it. Okay, I still think you might be wrong, but just because my stats didn't show it. Okay, and I love this. Like, if I were to, this is, ladies, listen to this. Like, you're going to prom, and I say, will you go to prom with me? And you really don't want to go with me, right? Will you go to prom with me? You really don't want to go. You're not going to say, I reject you, but you could say, I fail to reject you, right? But you never accept it, did you? So there's wiggle room in that, right? There's wiggle room. So when you accept, there's no wiggle room. Will you marry me? I accept. Or will you marry me? I failed to reject you. Do you see there's some wiggle room with failing to reject, right? If it's accept, you have a ring on your finger, end all be all. If you say I fail to reject you, there's some wiggle room, right? Okay, so we never accept. Accept is very definitive, right? So we never accept, we fail to reject. I might say accept loosely because it makes more sense to you guys in the beginning. So I might say, okay, we're going to accept that, which really means fail to reject. So just make sure that you understand that's what we're going to do in our decision. And of course, we're going to back that up with some statistical evidence. Okay? All right, let's do two problems. Here we go. We're going to do a greater than, less than, and then go from there. Okay? So read through the notes. Bum, ba-dum, ba-bum, bum. And here we go, 11.2. So this is the problem. I'm going to scad this whole thing out. I'm hoping all the information I need is on this one paper or this one slide. Bless you. You're going to find about 8 slides that have to do with this problem, okay? You're going to find a lot of slides out there that have to do with this problem. Like I said, I'm going to put it all together, okay? All right, so here we go. In one city, the mean response time to all accidents involving life-threatening injuries last year was 6.7 with a standard deviation of 2 minutes. Now look at that. That is a population standard deviation. That is a population mean. This is historically what we have found to be true. Okay? Now the city managers encourage the paramedics, fire department, and the policemen to do a better job. Come on, sugars, you can do faster than that, right? So they did that. At the end of the year, he took an SRS of 400 calls and got a mean response time of 6.48. Is this good evidence that the mean response time has decreased since last year? Okay? Has it decreased enough for me to believe that me saying go sugars go has made them make a difference? Okay? So is there statistical evidence to support it? So that is what we're going to come up with. Now, there are some key things we need to look at. So I'm going to go ahead. We have a mu. We have a standard deviation. We have an SRS of 400, large sample size, and an SRS. That's good. And now we have an X bar of 6.48. And then the very last thing they said was, did it decrease? Did it decrease? So now we are going to SCAD this whole bad boy. Are y'all ready? All right, this is your first significance test, so make sure that you're watching. Let me move this back a little bit so you guys can see the whole board. You still can't see the whole board. Sorry, sugars. All right, maybe not even. Wow, okay. All right, I keep moving it back and it's still not showing more, but that's okay. All right, so here we go. Set up. Do we believe that the mean response time has increased, decreased, or changed? Which one do we believe? Decrease. So we're looking at a decrease. A decrease is less than, right? That's a less than sign. So we're going to go ahead and do our setup. I'm going to try to stay on the board so everybody at home can see me. Our setup here is we have to do our ho and our ha. Go ahead and put little colons right there. Colon symbol. And now this is how you write your ho and your ha. It is based off your population mean. It either remains what we historically thought, so our ho is our null hypothesis. So either it has remained 7 minutes. And our alternative is that we believe that it has become less than 6.7 minutes. Now notice I'm using population mu and it does not change. Nowhere up here do I mention my X bar, because guess what? If I were to take another SRS of 400 and get another X bar, do you think it's going to be 6.48? Probably not. So what I'm saying is, all right, I know y'all are claiming 6.7. I just think it's less than 6.7. Okay? But I'm not going to use my one sample because there's going to be variability. So I'm not going to use my 6.48 up there. Notice the only thing that changes between these two is the symbol in the middle. The number's the same, the mu's the same. That's it. So the only thing that changes is the symbol in the middle. Are y'all good so far? All right, so now that I have that, I'm going to come down here and I'm going to do my conditions. So we're going to send our conditions. Is this an SRS?
Yes.
Yes, that was given to me. That's all you have to write. Yes, given. Independence, capital N is greater than or equal to 10N. So I have 10 times 400 calls. Capital N would be all the calls. Could we say that there might be more than 4,000 calls brought in? Yes. Or another way to do independence, and I think I talked to maybe Owen about this yesterday, is it logical that all of these car accidents are independent of each other? Each phone call, probably independent of each other. So you could on your independence, or is it logical independence? Yeah, sometimes it's just logical, okay? Yesterday on your quiz, when you had the runners problem, right? Wouldn't all of the runners' weights be independent of each other? Right? They're just independent of each other, okay? So that's just logical. And then what does N stand for?
Normality.
Normality. How do I find normality with an X bar problem? Yeah, N is greater than or equal to 30. Is that true? Yes, 400 is greater than or equal to 30, so we're good to go. All right, so all that should seem just about like we're used to, right? So now what we're going to do is arithmetic and decision. And I love drawing a picture when it comes to arithmetic. So here we go with arithmetic. All right, so our arithmetic, I'm going to draw a little picture here so I can see what's happening. Here is our mu, and our mu is 6.7. I know this is a less than problem. My X bar is at 6.48. Now, I've led you here before, so this should not feel too unusual. How likely is it for me to get 6.48 when the historical climb is 6.7? How likely is it for me to get a number that low or lower? I've got to find an area. So which area should I shade? I need to shade the area that is that low or lower, and then that will give me my p-value. So given that you have historically set at 6.7, how odd or unusual would it be for me to get a number that low or lower? So let's find the p-value. What's the probability of me getting 6.48 or lower than 6.48? So that's all I have to do. So here comes my arithmetic. Am I using a Z or a T? I'm using a z, right? Okay, so z is x bar minus mu all over sigma over the square root of n. So we have 6.48 minus 6.72 all over the square root of 400. All right, should I get a negative or a positive z-score? It's really still called a z-star here. It's a critical value, so it really is a z-star. Same thing we used in confidence intervals. And did you get negative 2.2? Anybody get negative 2.2? Y'all are going to go with it? Did you get that, Katie Perkins? Okay. All right, so negative 2.2. So now I have to come up with the p-value that is associated with that. All right, negative 2.20, 0.0139. So I get 0.0139. Move your decimal place 2 times. 1.39%. So 1.39% of the time, I would get an X bar of 6.48 or lower. Does that seem unusual?
Yeah.
Oh, you're already telling me the answer. Thank you. Thank you very much. All right, yes. So, do I believe, is this so far away? Think about it. Is it so far away from what your claim is that you're willing to reject this claim of 6.7 and say it must be lower than 6.7 now? Now, if it was really close, it would have a z-score close to 0, right? So if the mean has a z-score of 0, and if I was close to the mean, I would have a z-score that's really close to 0. Maybe 0.5, 1, 1.5. But how many standard deviations am I away? I am 2.2 standard deviations below average. If you're getting out 2 standard deviations, think about your 95% rule. You're getting far out there. There's only 1% left in the tail. So there is only, if HO were true, if the HO were true, I would only get a number this low or lower 1.39% of the time. That's pretty unusual. The smaller the p-value, the more evidence you have against the HO. If your p-value is large and you're creeping up towards the mean's at 50%, right? So if you get a 35% p-value or a 30% p-value or even a 20% p-value, that means you're pretty close to that mean. But if you get something so far out that you have a teeny tiny p-value, then that means that that's more evidence to reject the historical claim, okay? So since my p-value is so low, I'm going to go over here and write my decision. All right, so if HO were true, getting an X bar equal to 6.48 minutes would only happen 1.39% of the time. 1.39% of the time, that's pretty rare, right? That means there's no way that 6.7 can still be true because I got 6.48, and me getting 6.48 when your claim is 6.7 to be true would only happen 1% of the time, right? So therefore, I reject the HO, I reject HO, and when you reject HO, this is what you're doing. You're going to come over here, and when you reject HO, you can mark through it in your mind, which if you reject that, that means that you are concluding that your HA is true. So I reject HO and conclude the mean response time is now less than 6.7 minutes. Because if the HO were true, I would only get 6.48, 1.6 or 1.39% of the time if the HO were true. So since my X bar is so far away from their claim, then I know that their historical view can no longer be true. Okay? Now, how low can you go? How low must your p-value be? Okay? So Party Sabetti talked about this a little bit. Sometimes your employers will give you an alpha level. It's your rejection line. Okay? So you'll get an alpha level. You may have 5%, you may have 1%, you may have 10%. And they're saying if your p-value gets below my alpha level, okay, my rejection rate, if your p-value gets lower than that, then you're going to reject, okay? So if my alpha level were 5% here, well, my p-value is less than that, so I'd reject. I'm further in the tail than 5%. I'm lower than 5%, I would reject. I wouldn't reject at the 1% rate because my p-value is not as low as 1%. I would definitely reject at the 10%, okay? So sometimes they'll give you a significance level. They'll give you that rejection level, okay? So what I like to say is if P is less than alpha, then you're going to reject. So you can write that down. So if your P is less than alpha, then you're going to reject if they give you an alpha level, okay? Now this is called a one-tailed test. A greater than or less than, those are one-tailed tests. Now, those are the ones that we really like to do because they will really give you enough evidence. Sometimes if you're not sure which way it's going to go, your 16.9 ounce water, it sometimes overflows on you. Sometimes it seems really low. You don't know if it's greater than or less than. You just think that there is some issues going on with the water filling stations, right? You just think there's some issues going on. So you might not know if it's less than or greater than, so you would claim a not equal to. Now, the thing that kind of stinks about the not equal to is it's a two-tailed test. You don't know if it's less than or greater than, but it's a two-tailed test. So you have to use this p-value and this p-value, right? Well, if you're using this area and this area under the curve, you have two areas under the curve, then you're going to have a big p-value. It's going to be hard to reject, okay? All right, so let's look at one of those. All right, take a deep breath. How you doing? That's not that bad. It's not totally terrible. All right, so now I have to find the other problem that I want to do. It is on job satisfaction. So let's see if I can skip through this. There we go. All right, remember you have a null and an alternative. It can be one-sided or two-sided, one-tailed or two-tailed. All right, this is what we're going to do. I think I might have to move on to get some information on another slide. All right, so now we're going to do a two-tailed test and then we'll be done, okay? All right, so we have job satisfaction. So you're on an assembly line. I told you guys about, I used to take my kids to that, what was it called? Maplehurst Bakeries, where they make all the cakes. I used to take all my statistics kids there. Maplehurst Bakeries. We would see all the cakes that were made for Publix. It was amazing, right? But there was one lady that was machine paste. She worked on an assembly line. And do you know what she did? She put the muffin cups in the muffin cup holders all day. Muffin cups, the paper, the paper liners. That's what she did all day. And here's the assembly line moving, and she's like, put them in and put them in. Could you imagine? That's what she did all day. Now, she had a job, but that was her job, right? I don't know if I'd be super stressed out or just super dulled by any sensation. Do you know what I mean? Like, I don't know if I'd have anxiety about getting all the paper cups in, or it was moving slow enough that I would just fall asleep. I'm not sure. But anyhow, so here we go. Job satisfaction. People did assembly work. We have 18 subjects. One group was able to pace themselves. The other one was paced by the machine. So the machine was moving them along, okay? After 2 weeks, they took the job diagnostic survey and then switched work environments. So this is a matched pairs design, okay? We're doing machine paced, self-paced. We're trying to see which one is what's going on. So now look at this. This is a matched pairs. We did this in the last chapter where it was a T interval, okay? But it was the difference, so we had to subtract. So if you're trying to see if there's no difference in how people feel versus there is a difference, we're going to use 0. Okay? So next to this, sometimes it helps to write in words. No difference between machine and self-paced. A not equals to would mean there is a difference between machine and self-paced. I'm not really sure which one they want. I don't know if they're going to be happier this way or happier that way. So I'm using a not equals to because I'm not sure which one that they would prefer. I can't use a greater than or less than there, okay? So I'm going to go ahead and write down some information that we do know, and I'm going to scab this problem, but I am going to have to skip to another slide to get some more information. Like I said, the notes are everywhere. All right, so in my setup, I already know my ho and my ha. So mu is equal to 0, mu is not equal to 0, okay? So I already have that down. And I'm not really sure. I've got to do some subtraction here. I don't know if I'm doing machine minus self-paced should be 0 or self minus machine paced, which we'll get to in the next problem. Oh, it says right here, self-paced minus machine paced. Okay, so we're doing self-paced minus machine paced. Okay, and there is no difference between the two. That's what this means, okay? This means no difference. And then this means that self-paced minus machine paced, there is a difference. But remember, you gotta know, and I said this last chapter, you gotta know which direction you're going in. If you're thinking that they're happier self-paced, then shouldn't I get a number greater than 1? Or greater than 0? If I think machine paced makes them happier, then I would get a negative number, right? If I think self-paced, when I subtract them, is happier, then I get a positive number. So let's see what we're going to. All right, what else do I know? I do know that n equals what? What's my?
18.
N equals 18. All right, so I know n equals 18. All right, now let's go find our next slide here. Mean response time, mean response time. We already did that, mean response time. We know what our p-value is. That's mean response. Okay, mean response time, mean response time. Mean response time, see? Okay. Read this real quick and then I'll get back to the problem. If the p-value is as small or smaller than your alpha level, like I said, that's your significance level, then you're going to reject the ho and it makes it significant. The smaller the p-value is, the further you're in the tail, the further you are from their historical claim. So you're going to reject. All right, and we did that already. Quickly, you do need to pick your alpha level, your significance level before you run the test. Don't do the whole SCAD. You get down here and look at your p-value and I'm like, oh, I'm going to pick an alpha level that'll make this significant. No, you got to pick your alpha level at the beginning, okay? So don't bust out an alpha level later. Usually they'll tell it to you. You can apply your own alpha level if they don't give you one. All right, and where is my self-paced minus machine paced? I was hoping that that problem would pop back up somewhere. Did it pop? Oh, there it is, job satisfaction. All right, here we go. Here is our job satisfaction. All right, so back to our job satisfaction, and then we're gonna rock it. Okay, here we go. This is a two-tailed test. Now we know we have a sigma of 60. So find this problem. We had 18 workers. I got an X bar of 17. That is a positive number. Since that's a positive number, I know that they must prefer what? It's a positive number.
So,
Yeah, they must prefer self-paced. So if I drew a picture over here and I have my mu equals 0, okay, and this is self minus machine equals 0, no difference between the two, right, if I were to subtract them. And then over here, I get an X bar of 17, and that means self minus machine ended up being 17, then they must prefer self-paced over machine-paced, okay? Get that in your head so that you can explain the rest of the problem. All right, so we have our setup. Let's do our conditions real quick. What time is it? Okay. All right, so our S is our SRS. I'm not sure in this problem, but I would bet that they randomly assigned which one that got what treatment first, right? Did they get self or machine? So I'm going to assume that they use some sort of random allocation on this problem on who received which treatment. We can look in the book. Independence. Do you believe, now again, I'm not sure if I will actually be able to prove this because I don't know how many, the number of people that work at this business, but would you believe that their feelings on machine itself would be independent of each other? Yeah, I would absolutely believe that their job diagnostic survey that they took, that all JDS scores would be independent. Not like, hey buddy, what'd you put on your survey? I'm gonna put the same thing. No, they're just taking a survey about how they feel. All right, and then normality. Did I hit normality on this one?
No.
I did not hit the greater than or equal to 30. So there are some options. They could tell me that it's normally distributed, right? And they did not tell me. If they gave me data, I could do a box plot. And they didn't tell me that either. So I'm really not sure if this is normally distributed or if they would have given me that information. Like I said, I could look at this example in the book. All right, let's get to our calculations. You guys have sinned before. If I gave you all the information, you could probably send this bad boy up, okay? Let's get to the arithmetic so you understand how this is done, okay? So now I'm moving on to my arithmetic. And this is a sigma, so I'm going to do a z star, x bar, which is 17, minus mu, which is 0, standard deviation of 60 over the square root of 18 workers that filled out the survey. Yes, ma'am?
Why is it Z star? If you're just finding like the Z star, why
It's-
would you use Z star?
It is when you're doing inference, which means you're drawing a conclusion, then it's called a critical value. It's kind of like that cutoff value. Same thing with confidence intervals. They changed it to something called the critical value. It's kind of like like on a confidence interval, it was that end point, right? It's between here and here that it gives us an estimate, right? So a Z star gives us an estimate instead of just a place value for one thing. So they changed the name of it, even though it's kind of treated the same. But when you're doing inferential statistics, they call it a Z star. So I know that's not the best answer, but they do change it when you start doing inference. All right, so here we go, even though it's really treated the same. Let's put this in. Did anybody put this in yet? What'd you get? 1.2? Okay, so I get 1.2, okay? Now, the bad part about this is our Z star 1.2, so I know that this is 1.2 standard deviations above the mean. But since this is a two-tailed test, and I did not have the intuition at the beginning whether to make this a greater than or less than, I actually have to make it a two-tailed test. Now your X bar is gonna either land above or below. There's only one X bar, right? But because I did not know which direction to go in, I have to make this a two-tailed test because I couldn't make the decision at the beginning to make this a one-tailed test. Okay? So wherever that Z falls and that p-value, because it's a two-tailed test, you have to multiply that p-value times 2. Okay? Because we're also looking at the chance of it falling down here at negative 1.2, which would give you the exact same p-value. Okay? So whatever I get down here for this p-value, because it's a two-tailed test, you have to multiply your p-value by 2 because it's a two-tailed test. All right, so let's look up 1.2. Wouldn't this be an above problem? But couldn't I really look up negative 1.2? Isn't it the same thing, right? So I'm going to look up negative 1.2 and then just double it. So I don't have to do 1 minus p and all that junk, okay? So negative 1.2 is 0.1151. But because it's a two-tailed test, it's a not equals to, which is a two-tailed test, I have to multiply this times 2. .2302. So move that over. That is 23, approximately 23% of the time. I would get an X bar of 17 self minus machine paced if there were truly no difference in people's feelings on their pace. Okay? 23%, that's not a teeny tiny p-value, is it? No, not at all, okay? So again, you could have an alpha level. Some of those alpha levels are 1%, 5%, or 10%. And if your p-value is below any of those, then you would reject. That means you're really far in the tail if you get a p-value of 5% or 1%, right? I got a p-value of 23%. That is not a whole lot of evidence to reject the hoe, okay? So my decision will be, I fail to reject the hoe. Okay? And I can put my p-value in parentheses. There's a bunch of different ways to write this. I did give you a sheet of paper last chapter on it, and I do have some extras if you want to work on your lingo of how to write your decision. Okay? So p equaling 23.02 and conclude. Now, if I fail to reject the hoe, then that means that's what I have to say. I fail to reject the hoe and conclude there is no difference in JDS scores for machine minus self-paced. And I'm sure there's a little bit of a prettier way to say that, but that is basically what we're saying. There is no difference in job satisfaction between machine-paced and self-paced. Okay? All right, I am done. All right, let me give you your worksheet for tonight. I did post it on Google Classroom too, okay? All right.